electrospray, ionization, and the matrix. Free your mind.
Unfortunately, no one can be told what the matrix is. You have to see it for yourself. This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes.
The blue pill says, protonation states in electrospray are determined by solution chemistry. Basic termini of tryptic peptides will enhance ionization efficiency. Acidic buffers in electrospray will enhance protonation. The higher charge states for denatured proteins that we always see result from more basic residues becoming solvent accessible. The multiple charge states we always see in electrospray of proteins arise from multiple protein conformers. And ionization under native conditions is a gas phase artifact. That's the blue pill. So what about the red pill? Well, as Morpheus says, you have to see it for yourself. So let's see some electrospray data. Here we have plotted the charge state for a range of peptides. These are BSA tryptic and chymotryptic peptides. And what we've done here is plotted the charge state against the number of basic residues. We're looking for a relationship here. What you can see is there isn't really any relationship there at all. I mean, you can conclude that basic residue count for these tryptic and chymotryptic peptides is a very poor predictor of charge state. However, if we take the same set of peptides and we plot the charge state against the residue count, what we find is this appears to be a very good predictor of charge state. Those are peptides. This is a protein. This protein is pepsin. It's enzymatically active, and this is a native spectrum, a native electrospray spectrum, and I've shown you here the sequence of pepsin, and you can see that pepsin has just 3 basic residues, and it will also have a basic charge at the N terminus. So pepsin has just 4 charge groups in solution. However, when you look at the spectrum, you can see that the maximum charge state here, the maximum protonation state for pepsin is actually plus 11. So native pepsin has 7 more protons than you would predict. If we denature pepsin, we see now, this is the same sequence, we see now that we have a large number of charge states, and the maximum protonation state for pepsin under denaturing conditions is plus 47. So denatured pepsin has 43 more protons in electrospray than predicted. And that's a protein. This is an oligonucleotide. So this is a nucleic acid. Nucleic acid should not ionize at all in ion mode. What you see here is, in fact, they do. And not only that, the signal for oligonucleotides in positive ion mode is about 50 times stronger than in negative ion mode. And also we have an additional +5 charge state. There is nothing remarkable about these examples. So here we plotted the difference between the maximum protonation state and the protonated residue count for 38 randomly chosen proteins. What we would expect is that the number should be the same, or there should be fewer protons in electrospray than those in solution. What you actually see is almost all proteins have more electrospray protons than you would predict. So, what is going on? Some years ago now, this experiment was done. What these authors did is they took around 20 model proteins, and they calculated the solvent accessible surface area, and they plotted this against the average charge state, the average native charge state in electrospray. So this is this measurement here. And what you can see is there is almost a perfect straight line. And perfect straight lines don't really happen in biology. It's something I would associate with physics. So this experiment shows that the native charge state for a protein is dependent on its surface area. So as I said, this experiment was done some 17 years ago. It's largely been ignored. People in the field are aware of this result, but it's not really discussed. Well, why is that? Well, science is done by human beings, and I would say humans, they usually see what they are expecting to see, not what is actually there. And I want to illustrate this point with a little short video. This is an Ames room. I should say this video has not been manipulated. Obviously, it's an optical illusion, but it's not what you are expecting. One group that took this result at face value, they decided that if the charge state in electrospray for native proteins is determined by the surface area, then the same thing should hold for unfolded proteins. So they took this measurement here, the average charge state for a denatured protein, and they plotted it against their calculation of the surface area, and there is an approximate relationship here with the black dots, but it's not massively convincing. We did a slightly different experiment. What we did is we took 65 denatured proteins and we measured the maximum charge state here, and we plotted this against the residue number for these proteins. And what you can see is there is almost a perfect straight line relationship with these. However, we do have some outliers. There are 8 outliers in this data set. They're marked in green. All of these outliers, these are the only proteins in our data set which have disulfide bridges. Reduce those disulfide bridges, then all of these proteins will then fall onto this regression line. This final 9th protein, this final outlier, this is a cyclized protein. So it's a spy-tag, spy-catcher, cyclized protein, and it cannot linearize. So this experiment shows very clearly that the surface area dependence of denatured proteins corresponds with So this experiment shows that there is a perfect relationship between the maximum charge state for a protein and the number of This experiment shows that there is a perfect correlation between the maximum charge state for a denatured protein and the number of residues. This is not actually new data. If we go back to 1991, this is a meta-study of over 200 proteins, denatured proteins and peptides, and we plotted this, this data as we've done before. So this is the maximum charge state against the molecular weight, which is similar to the residue number, and again, we get a very convincing straight line relationship. So the existence of this relationship has actually been known for over 30 years. One thing this relationship tells us is that the maximum electrospray charge state, the charge density, cannot exceed MZ600 for biopolymers, and this is irrespective of the number of charge groups. And I can illustrate this with a very, very basic peptide. This is a histone tail peptide. It's a denaturing spectrum. You can see from the sequence that there are 16 basic residues, but the maximum charge that these can carry is +9, and that corresponds to MZ600. So what does determine electrospray protonation state? Well, I can illustrate this with an experiment done with two different proteins. The protein on the top two traces, this is myoglobin. This protein will unfold under denaturing conditions, and that's what you can see happening here. This is the native spectrum. We have two sets of peaks here because we have a holoprotein and the apoprotein. This is the free heme. When we denature this protein by dropping the pH to pH 2 in methanol, we have this typical charge distribution for a denatured protein. If we compare that now with the same experiment, this time done with lysozyme, lysozyme has 4 disulfide bonds. It cannot linearize. When we expose it to the same conditions, these are native conditions, pH 6.5. Under denaturing conditions at pH 2 and in methanol, there is almost no change. So what this tells you is the protonation state is determined by the degree of unfolding, not by the buffer pH. Of course, the buffer pH can influence the degree of unfolding, but that's not the primary determinant of the charging. The primary determinant of charging is the amount of, is the surface area. So where do these proteins come from? If they're not coming from the pH of the buffer, where are these positive ions coming from? Well, you need to understand that in electrospray, the ion source, this functions as an electrochemical cell. So what's happening here at the electrospray tip is protons are being generated by electrolysis of water. These proteins are always going to be in excess, and they will be in excess for species above the Rayleigh limit. This is 600 Daltons, and this will be irrespective of the mobile phase pH. So the charge, the electrospray charge on a protein is a direct measurement of its surface area. And I can illustrate this with a simple experiment with BSA. So this is BSA under native conditions, and this is a typical native ion distribution and low charge state, few charge, a few charged, small number of peaks, and the protein is correctly folded. If we compare this now with an aged preparation of BSA, you can see we still have the native protein, the native distribution, but we have a new distribution here now, and this represents partially unfolded BSA. Now we can completely denature the BSA, that's what we've done here in 50% methanol, 0.1% formic acid, pH 2. And now we have the charge states pushed towards the left, much higher charge states and more of them. But the BSA is not fully denatured because it still has 19 disulfide bonds. If we break all those bonds, then BSA is now able to linearize and we achieve the highest charge state. So what you're seeing here is increasing degrees of denaturation, and this corresponds to higher and more abundant charge states. I can illustrate this even better by an experiment done here. So this is an ion beam deposition experiment, and in this instrument we are able to isolate different charge states, and then they are decelerated and deposited onto a surface where they can then be imaged. And what you can see here is the high charge states, plus 19, plus 18, plus 17. These are coming from the linearized polypeptide. As the charge states decrease, the polypeptide becomes more folded until the lowest charge states are the smallest surface area of the most folded protein. So this experiment shows that charge state is determined by surface area, and the surface area is determined by protein folding. So it turns out that is really, really useful thing. There is a charge radius equation that has been developed, and this allows us to calculate the size of a protein if the protein is a globular protein, and we assume that that globular protein approximates a sphere. And this is a protein which actually makes a perfect sphere. So this is a complex. It's a 60-mer complex with a molecular weight of roughly just under 900,000. This is a native spectrum, and this complex forms a perfect hollow sphere. We know this because we have a crystal structure for it. We also have Sachs data for it, and we know that it is a perfect Buckminster fullerene. If we take the native spectrum and we take the average charge state of this native spectrum, plus 79, we put it into this formula, we get a radius measurement of 85.8 angstroms by native mass spec. If we compare that with the radius measurement from the crystal structure, you can see it's almost exactly the same. So this is telling us that the charge radius equation is valid for a perfect sphere. We can do a similar experiment using measuring the hydrodynamic radius of a range of model proteins and compare this to the charge radius. So here we plotted the charge radius in angstroms against the hydrodynamic radius determined by size exclusion chromatography, and we have a pretty good relationship. So the charge radius equation is valid for globular proteins in solution. You would not expect this to be a perfect straight line because these proteins are not perfect spheres, but this approximation is fairly good. And this also applies to the gas phase. So this is a comparison of collisional cross-sectional area against the native charge state for 15 model proteins. And you can see that the charge radius equation, this is also valid for globular proteins in the gas phase. This is a special case. Sonic hedgehog is a monomer and a dimer. And so you can see monomer and dimer charge distributions. These are unusual in that these distributions overlap precisely. So the monomer distribution, here we've got the M1Z9, overlaps the dimer M2Z18, and this is unusual. The only way you can explain this distribution in terms of surface area and charge is that if this is the charge on the monomer, there are two ways to achieve a dimer. We can either have a single point of contact on the dimer here, or we can have multiple points of contact. But in order to achieve exactly double the surface area, exactly double the charge, you have to have this structure. Okay, so a single point of contact. Overlapping charge distributions mean just that, a single point of contact for the dimer. When we look at the crystal structure for sonic hedgehog, that's exactly what we see. So that's also really useful. The dynamic charge radius plots can be used to monitor changes in conformation. And we've done this here for Aurora kinase. So Aurora is a kinase. It can auto-phosphorylate. So when it's incubated with ATP, it acquires phosphorylation groups. So here we plotted the dynamic charge radius for phosphorylation state 0. We plot this for phosphorylation state 1. There isn't very much difference. Phosphorylation state 2, there's a slight difference. Again, it's not much. However, when we plot phosphorylation state 3, we can see the charge distribution has shifted. And the same applies for state 4 and state 5. So what we're looking at here is a 1% increase in surface area, which is happening as a result of conformational rearrangement that happens between phosphorylation state 2 and phosphorylation state 3. We can see the same phenomenon here. This it is an enzyme, MTHFR. It's a dimer. And what we have done here is plotted the dynamic charge radii for the phosphorylated protein and the dephosphorylated protein. And what we see is that dephosphorylation causes a shift in the conformation, making the protein have a larger surface area. So dephosphorylation for MTHFR induces a conformational change and an increase in charge radius. So why do we see multiple charge states? We always see multiple charge states for proteins, regardless of whether they are native or whether they are denatured. So why does this happen? So we can answer this question by comparing different classes of protein. Here we have denatured protein, and what we've done is we plotted the charge state against the residue count, and you can see we have a distribution of charges at for any particular protein. So this is a denatured protein with unrestricted molecular motion. If we compare that now to a native protein, native proteins, they have restricted molecular motion. So here we can see that the charge state is much, much narrower. Compare this now to this data set. This is coming from diphenylalanine self-assembled fibrils. So they are protein-like in terms of their chemistry. However, they are completely unlike proteins is that they are crystalline. So these structures are completely rigid. They have no molecular motion. And what you can see is each of these diphenylalanine fibrils, for each mass, there is a single charge state only. So molecular classes with the same chemistry, but different degrees of intramolecular motion are displaying characteristic charge state distributions. I can show you another example of this. This is a comparison of a highly stable protein with an intrinsically disordered protein. So streptavidin is the most firmly stable protein known. If we look at the native spectrum for streptavidin, we can see effectively there's really only one charge state, which is +16, and these other charge states are relatively minor. So if you measure the full width half maximum of this distribution, it approximates 1.5 charge units. Compare this now to tris tetraproline. TTP is an intrinsically disordered protein. It has no thermal melt curve. The spectrum you see is a native spectrum, and here you can see a broad and flat distribution of charges. And if we measure the full width half maximum of this distribution, this is 8 charge units. So proteins with different degrees of intramolecular motion display characteristic charge state distributions. So charge state distribution width, this measurement full width half maximum, can be used to measure changes in internal molecular motion, in other words, thermal stability. And we've done this here with a peptide. So this TAT peptide, these peptides are tridendrimeric peptides, so they have the 3 peptide strands linked together. And I'm showing you here 2 groups of peptides. We have cyclic and linear peptides. So the cyclic peptides are, the linear peptides are these 2 here, and the cyclic peptides are these 2 here. And we're plotting the normalized ion intensity against the peptide charge state. If we measure the full width half maximum for the linear peptides, we get this value of 3.2. Compare this to the circularized peptides, which are less mobile. They have a full width half maximum of 2.5 charge units. So circularized peptides are less flexible and they possess narrower charge distributions. Here's a similar experiment, this time done for a protein. This is trypsin. And what we have here, we plotted the normalized ion intensity against the calculated charge radius. And this is active trypsin at pH 8. If we measure the full width half maximum, it's 4 charge units. If we stabilize the trypsin, we're not denaturing it, we're just stabilizing it by lowering the pH to pH 1. pH stabilized trypsin has a narrower charge distribution of 2.5 charge units. And there's a third experiment we can do. We can do chemical stabilization. This is done by methylating the trypsin. And the methylated trypsin, which is chemically stabilized, this has a similar narrower charge distribution of 3 charge units. So this is very interesting, but how can we explain this? We need to explain this. So we can explain this with a new model of electrospray. We've called this the electrostatic charging model. And what it says is an excess of protons is always available for species above the Rayleigh limit. This is roughly 600 Daltons. And these protons are mobile and they will obey Coulomb's law to achieve minimum free energy. So it's a very simple model, and this is exactly what's happening in this picture here. Protons are mobile, the electrons are mobile, and they are obeying Coulomb's law to achieve minimum free energy. So our model conforms to the Thompson problem. So the Thompson problem, this determines the minimum electrostatic potential for a fixed number of charges constrained on the surface of a sphere. And they will repel each other with a force given by Coulomb's law. So what we've done here is we have plotted the minimum free energy against the charge radius for a series of spheres. And what we see is a charge radius calculation, Z equal to the radius to the 1.5 power. This conforms to and is a special case of the Thompson problem. So we are actually now able to explain all MZ spectra. And how we do this, this is for a native protein. So in a native protein, surface area is continually changing due to its molecular motion in solution. If we are able to plot the surface area for all the molecules at the same time, we would expect a surface area distribution. If we then bin that surface area distribution into integers, the distribution would look like this. But of course, these integers are protons, and the distribution actually looks like this. So this is a real spectrum for a native protein. The situation for denatured proteins is similar but slightly different. So here we have denatured protein, and its surface area is continually changing due to extensive and random molecular motion. If we plot that, if we were able to plot the surface area, this has an absolute maximum because we can't extend the protein beyond its linear fold. So we would expect a skewed surface area distribution like this. But of course, we need to plot the inverse of surface area because we plot mass over charge. Charge is related to surface area, so we need to plot the inverse, and it would look like this. We bin it into integers, it would look like this, and then we compare that to real data, where these integers are protons, and it looks exactly like this. This is exactly what we'd expect to see. So, are electrospray protons really mobile? Well, yes, they are. If you do this experiment, you look for singly charged peptides of BSA. What you discover is they can fragment from both ends. So we have a B ion series. We also have a Y ion series. So only charged peptides can be detected, so that this means that protons must be at opposite termini of the peptide. If we look at infrared photodissociation spectrum for cytochrome C, we see something interesting. This is only visible in the gas phase, but we see that this particular wavelength, we can see that this peak is associated with increasing positive charge state, with increasing protonation. So this 1483 centimeter waveline, this is only visible in the gas phase, and it is charge state dependent. So the red pill says that protonation states in electrospray are determined by surface area and surface area only. Basic acidic residues within the sequence have absolutely no influence. This means the electrospray protonation state is completely independent of pH. The higher charge states that we observe for denatured proteins, these arise from their greater surface area. And multiple charge states arise from surface area changes due to molecular motion. What this means is that ionization in native mass spec reflects solution phase conditions. That's all I want to say. If you enjoyed this video and found it useful, please tell your friends. If you want to know more about this topic, you can read it at this website. If you want to know more about mass spec itself, please visit my YouTube channel, and thank you for watching.